Yeah, all right.
So here's our tracker document. Here you can see we use two different models to model the motion of this Astro Blaster. This was because it's super hard to model a collision. So we use the red ball on the really top to follow here. And this one on the right is the motion of the ball just as we dropped it. So just covered new gravity. This one over here on the left is our graph that we have for the motion after it collision as it shoots straight up. So step through here one by one, you can see they're both matching here. And then as impact, switch over to this on the left, and then it follows this motion just as a projectile, follows it back down, like that. Yeah, and see for that one, in order to get this to match up perfectly, we used a statement here. It says if t is, which time is less than 0.1 second, it's moving at constant velocity. So, let's see, before it passes, there's no active gravity, and then as soon as they make up, it matches. That's how we got it to match up really well.
There you go. Okay, so you have to aim the gun way up here somewhere. So the way we figured that out is, well, drag force is something like the drag constant times drag coefficient times cross-sectional area times the density of the air times velocity squared. So we put this in the tracker, and we weren't sure what the drag coefficient was. We calculated the cross-sectional area of the monkey, and we got the air density online. So what we did was we videotaped the monkey just dropping by itself, and then we matched it. Then we put that on tracker, and we just trial and error the drag coefficient until we could find one that matched the falling monkey, and it came out to be 1.2, which is pretty darn high. So the monkey has two forces acting on him, a downward force and an upward force, keeping him from matching the ball. And we gave the ball a little bit of a drag coefficient, just 0.1, which is standard drag coefficient for a smooth sphere. And then we took the two models and put them on the same tracker file and moved them so that this one was a certain distance away. We kept the angle at 45 degrees. We moved them so that they both had the same time and position when they hit. And so this was aimed quite a bit higher. And then when we tested it, it worked out surprisingly well.
So the first, what you see here with the axes and where the gun is and where the monkey is, this was all predicted by tracker. This is something where when we found the drag coefficient of the monkey falling, we are able to line it up with the gun's projectile predicted motion. All we had from the gun was how fast the velocity was and what angle it was shooting at. And then with the monkey, all we had was the fact that it's falling in pretty much straight down, and it has some kind of drag coefficient that we determined experimentally. But it worked pretty well, and I'm really impressed with how accurate this actually was able to follow the motion, because we didn't tweak it afterwards to make it work. So here it goes. That's the ball following the motion. It drops a little bit lower than predicted, and I'm not sure why, but then it hits the monkey. And you can see that the monkey, up until that point, it's pretty much following the very top of the copy filter all the way down until it gets hit by the ball, and then the copy filter collapses and loses, or the drag goes away. A lot of the drag goes away.
Cross-sectional area just got reduced by it.
Right. So now you can see that it falls much faster towards the end, while it's still pretty much following the ball exactly where it was.
Down an inclined plane, And once it fell off this point here, it just became a projectile. So the force that was acting on it was just normal force of friction, gravity, and once it got to this point here, all the forces, the only force that was acting on it was just gravity. Equation becomes zero, and at that point it just becomes negative mg, which is just the ball falling in the right direction.
So you put the origin of the coordinate system at the starting point of the ball energy?
Yeah.
So this, okay.
The point and the conservation of energy should hit the spring and return back to the same point, but because of friction it doesn't, and it will move.
Alright. So we had it all set up in variables first, so we can play with it in tracker, but first we set up our mass with our spring, and we had our force equations. We had normal force, gravitational force, the friction force, and our acceleration was that direction at first. And then we had it set up where we hit the block, this match of the spring before compression, and the spring applies the second force on it. And we use those to plug in the tracker and set up a model on tracker that was just generic. We can plug in and mess around with the variables and use it to predict the different effects if we changed our theta or changed our mass and our spring constant. And then we videoed it.
Here's our video and the parameters. We just have gravity, theta, the spring constant, and xs is just the distance from here to the front of the spring, and mu and the normal force. And we measured the spring constant to be about 700, and I think it's about right. And so here's our it's a little bit off, but that was like the best we can get. Yeah, so.
You guys tried to experimentally find your spring constant?
Yeah, we did. We had our spring and then we put weights on top of it and just measured the compression each time.
Like the same thing we did in the lab, reversed it.
Yeah, we used two if statements. We had to put one for the frictional force. So when we said that when the velocity is negative, that the frictional force was going to be positive, and if the velocity was positive, then frictional force is negative. And there's another one. If x was less than xs, then we have the spring force k times x, and if it's not less than xs, then it's 0.
We settled on a physical pendulum system. The one we looked at the end part of the lab, where you've got this metal cylinder, big metal cylinder, and it's oscillating on some pole, which is another pole, like so. And so, our question was, essentially, if you have this oscillating initial amplitude, is it going to exhibit simple harmonic motion, which is what we would expect theoretically. But once you have the calculation for the period of motion, you should be able to get the omega, the angular frequency, and use that in the simple harmonic motion equation to see if it matches. And in fact, after fooling around with the inertia, we eventually got it to match fairly closely. It does seem to exhibit
yourself on the motion.
Okay, so here's our analytical particle model, and here's our parameters and equations, inertia and our radiuses, and our angular frequency, and then here's our simple harmonic motion equation, and if I play this, as you can see, it follows the pendulum fairly well. And yeah, I guess that's it. Is there anything else you want to add?
Questions?